You know, when Umesh invited me to attend this event, I got really excited. I saw all the speaker list, and I thought, great, I'll go and I'll talk about something. And then I ran into a problem, which is that a lot of the technical work that you're doing at OpenAI I actually can't talk about. So I was really racking my head, what could I talk about? Right now, so as of not too long ago, I switched all my focus to working on AI alignment, all my research focus, and we'll have very cool results to show there, but not just yet. So I'm like, okay, so this would have to be for the next talk, but what would be good for this talk? And I came up with something. I'll tell you about some very old results that we had at OpenAI many years ago, back in 2016 even, which really affected the way I think about unsupervised learning. And I thought I'd share them with you. It is possible that at this point you'll all find them obvious, but maybe not all of them. So there is at least a small chance that you'll find it interesting. So I want to set the expectations modestly and then hopefully exceed them. So a theory of unsupervised learning. How can such a thing exist? So, okay. Before we talk about unsupervised learning, we want to talk about learning in general. What is learning and why does learning work at all? Why should learning work at all, and why should computers be able to learn? And now we are just used to the fact, we take it for granted that neural networks learn, but why do they? Like, mathematically, why should they? Why would data have regularity that our machine learning models can capture? So that's not an obvious question. And one important conceptual advance that has taken place in machine learning many years ago by multiple people was the discovery and the formalization of supervised learning. So it goes under the name of pack learning or statistical learning theory. And the nice thing about supervised learning is that it gives you a precise mathematical condition under which learning must succeed. You're told that if you have some data from some data distribution, that if you manage to achieve a low training loss and the number of your degrees of freedom is smaller than your training set, then you will achieve low test error. And you are guaranteed to do so. So you have a mathematical condition where you can say, well, if I did find a function out of my function class which achieves low training error, then learning will succeed. And you can say, yeah, this is a very sensible mathematical thing that we can reason about. And that's why supervised learning is easy. And then you had all these theorems, which I thought were simple. You know, I found them elegant. You've seen maybe theorems like this. If you have your, basically it's like, this is the sort of thing where if you know it, you're going to say, oh yeah, that thing. And if you don't know it, it will not be possible to explain it in 30 seconds. Though it is possible to explain it in 5 minutes, just not 30 seconds. None of this stuff is complicated. And you've got your little proof, which says, well, if you have some number of functions in your function class, the probability that your train error will be far from your test error for at least one function, there is some math. And the math is simple. This is all the math, 3 lines of math. So 3 lines of math can prove all of supervised learning. Well, that's nice. That's very nice. So supervised learning is something that is well understood. Comparatively speaking, well understood. We know why it must succeed. So we can go forth and collect large supervised learning data sets and be completely certain that models will keep getting better. So that's the story there. And yeah, I forgot to mention a very important piece of this result. The test distribution and the training distribution need to be the same. If they're the same, then your theory of supervised learning kicks in and works and will be successful. So conceptually, it is trivial. We have an answer for why supervised learning works, why speech recognition should work, why image categorization should work, because they all reduce to supervised learning, which works, which has this mathematical guarantee. So this is very nice. Here, I want to make a small side comment on VC dimension to those of you who care about such things. There may be a small subset, so if you want to zone out for the next 30 seconds, feel free to do so. So a lot of writings about statistical learning theory emphasize the VC dimension as a key component. But the main reason the VC dimension, in fact, the only reason the VC dimension was invented was to allow us to handle parameters which have infinite precision. The VC dimension was invented to handle precision, like parameters with infinite precision. So if you have your linear classifier, every parameter has infinite precision. But then, of course, in reality, all our floats are finite precision, and their precision is shrinking. So you can, and you could, so you have your, so the number of functions that are implemented by a computer is actually small, and you can reduce it back to the this little formula, which gives you pretty much all the best bounds that you can get from supervised learning. So I find this to be cool. I find this to be appealing because you have fewer lines of proof. Okay, now let's talk about unsupervised learning. So I claim, first of all, what is unsupervised learning? What is it? Supervised learning is like, yeah, you've got your data that says, here, do this, here, do that, and you have all this data. You do well in your training error is low. You have more training data than degrees of freedom in your function class, parameters, but maybe other things too. Degrees of freedom, like bits. And you say, okay, your supervised learning will succeed. But what is unsupervised learning? What can you say at all about unsupervised learning? And I'll say that at least I have not seen like an exposition of unsupervised learning which I found satisfying. How to reason about it mathematically? We can reason about it intuitively, but can we reason about it mathematically? And for some context, what is the old dream of unsupervised learning? Which, by the way, this dream has been fulfilled, but it's fulfilled empirically. Like, can we go just a tiny bit beyond the empirical results? Like the idea that you just look at the images or you just look at the text without being told what to do with them, and somehow you still discover the true hidden structure that exists in the data, and somehow it helps you. But why? Why should it happen? Should it happen? Should we expect it to happen? You don't have anything remotely similar to the supervised learning guarantee. The supervised learning guarantee says, yeah, like, get your low training error and you're going to get your learning. It's going to be great success. Unsupervised learning, it appears that it's not this way. And like people were talking about it for a long time. In the 80s, the Boltzmann machine was already talking about unsupervised learning. And unsupervised learning also did not work at small scale. But the old ideas were there, like the noisy autoencoder. To those of you who remember it, it's like BERT or the diffusion model. Like within it, it's a tiny twist, the tiniest of twists. The language models of all times, they also, generated cool samples for their time, but their unsupervised learning performance was not as impressive as those of today. But I want to make the case that it is confusing, because it's like, why is it confusing? You optimize, like, how does unsupervised learning work? You say, okay, let's optimize some kind of reconstruction error, or let's optimize some kind of denoising error, or like some kind of self-supervised learning error. You optimize one objective, right? Oh yes, I just said that. But you care about a different objective. So then doesn't it mean that you have no reason to expect that you'll get any kind of good unsupervised learning results? Or rather, you do get them empirically, but like, is it going to be, like, the level of mystery is quite high, I claim. Like it seems like a totally inaccessible phenomenon. You optimize one objective, but you care about another objective. And yet it helps. How can that be? Magic. Okay. So yeah. The other thing, by the way, is that well, I guess I'm gonna say something which is only 90% true. Unsupervised learning doesn't. You could say, okay, so you just learned the structure in the input distribution and it helped you. But then, what if you're training from the uniform distribution? Then all your unsupervised learning algorithms will fail. How should you think about that? So what can we say? Do we need to make assumptions? What kind of assumptions? So I'd like to present potentially a way of thinking about unsupervised learning, which I think I personally find it interesting. Perhaps you'll find it interesting too. Let's find out. So I want to show you one way of doing unsupervised learning, which is not necessarily widely known because it never became the dominant way of doing unsupervised learning. But it has the cool feature that, similarly to supervised learning, it has to work. So what kind of mysterious unsupervised learning procedure, where you're not given any labels to any of your inputs, is still guaranteed to work? Distribution matching. Distribution matching. So what is distribution matching? Say I've got my data. I've got X and I've got Y. My data sources. There's no correspondence between them. Just got two data sources. Data source X and data source Y. Data source Y. Language 1, language 2. Text, speech. No correspondence between them. Let us look at this criterion. Find the function f such that the distribution of f of x is similar to the distribution of y. It is a constraint on f. And in the case of machine translation and speech recognition, for example, this constraint might be meaningful. Like you could say, yeah, if I have like long sentences, if you tell me that you have a function such that the distribution, you take your distribution of English sentences, you apply the function f to them, and you get something which is very similar to the distribution of French sentences, you can say, okay, I found the true constraint about f. If the dimensionality of x and the dimensionality of y is high enough, that's going to give you a lot of constraints. In fact, you might be able to almost fully recover f from that information. This is an example of supervised learning, of unsupervised learning, where it is still guaranteed to work in the same sense that supervised learning is guaranteed to work. Also, substitution ciphers, like little simple encryptions, will also fit into this framework. So that's the thing, like, okay. And so like, I ran into this. I've independently discovered this in 2015. And I got really fascinated by it because I thought, wow, maybe there is something meaningful, mathematically meaningful, that we can say about unsupervised learning. And so, but let's see, the thing about this setup is that still it's a little bit artificial. It's still, real machine learning setups aren't like this. And the way we like to think about unsupervised learning isn't that also. Okay, now I'll present to you the meat of what I wanted to say. How a proposed way to think about unsupervised learning that puts it on par with supervised learning. It says, okay, what is it doing mathematically? How can you be sure that your unsupervised learning is good? Compression to the rescue. Obviously, it is well known. I shouldn't say obviously. It is not obvious, but it is well known that compression is prediction. Every compressor can be turned to a predictor, and vice versa. There is a one-to-one correspondence between all compressors and all predictors. However, I would argue that for the purpose of thinking about unsupervised learning, the language of compression offers some advantages. At least for me it did. Perhaps it will for you too. So consider the following thought experiment. This thought experiment is the most important slide. Say you have two data sets, X and Y. You have two data sets, two files on your big giant hard disk. And say you have a really great compression algorithm, C, which takes data in and outputs compressed objects out. Say you compress X and Y jointly. You concatenate them. You take the two data sets and you concatenate them and you feed them to your compressor. What will happen? Well, let's see. What, and in particular, an important question is, what will a sufficiently good compressor will do? My answer is, very intuitively, it will use the patterns that exist inside X to help it compress Y, and vice versa. You could make the same claim about prediction, but somehow it's more intuitive when you say it about compression. I don't know why that is, but I find it to be the case. So that's our clue. And you can make an equation like this, where you say, hey, if your compression is good enough, if it's like a real great compressor, it should say that the compression of your concatenation of your giant files should be no worse than the separate compression of your two files. So any additional compression that was gained by concatenation is some kind of shared structure that your compressor noticed. And the better your compressor is, the more shared structure it will extract. The gap is the shared structure, or the algorithmic mutual information. So that's interesting, right? You can see what I'm alluding to. Y is the data of your supervised task. X is your unsupervised task. But suddenly, you have some kind of mathematical reason for the information, for the patterns in X to try to help Y. Notice also how it generalizes distribution matching. If we are in the distribution matching case, where you've got your X is language 1 and Y is language 2, and you're saying, and you know that there exists some simple function f that transforms one distribution into the other, surely your compressor, if it's good, will notice that and make use of that, and maybe even internally try to recover this function. I think that's pretty cool. We've closed the circle. So how do we formalize it then? What will be the formalization of unsupervised learning? Let's see if I can do it. Consider an ML algorithm. So here, by the way, in what follows, I'll be a bit sloppy, and I will use compression and prediction interchangeably. Say you have a machine learning algorithm A. It's an algorithm A, and it tries to compress Y. And say it has access to X. X is file number 1, and Y is file number 2. You want your machine learning algorithm, your compressor, to compress Y, and it can probe X as it sees fit. The goal is to compress Y as well as possible. We can ask ourselves, what is our regret of using this particular algorithm? Do you all see where I'm getting at? Regret relative to what? If I do a good enough job, if I have, being low regret means that I've gotten all the help that I can possibly get from this unlabeled data. This unlabeled data has helped me as much as possible, and I don't feel bad about it. I don't feel bad. I don't feel like I've left some prediction value on the table that someone else with a better compression algorithm could have used. That's what it means. And in particular, it's you can go and you can sleep happily at night knowing that if there is some information in the unlabeled data that could help my task, no one else, no one could have done as good of a job as me. I've done the best job at benefiting from my unlabeled data. So I think that is a step towards thinking about unsupervised learning. You don't know if your unsupervised data set is actually useful, It may be super useful. It may have the answer. It may be totally useless. It may be the uniform distribution. But if you have a low regret unsupervised learning algorithm, you can say, whether it's the first case or the second case, I know I've done my best. I know I've done my best at benefiting from my unlabeled data. And no one could have done better than me. Now I want to take a detour to theory land, which is a little obscure. I think it is interesting. Kolmogorov complexity as the ultimate compressor gives us the ultimate low regret algorithm, which is actually not an algorithm because it's not computable. But you'll see what I mean really quickly. So Kolmogorov, first of all, like for some context, who here is familiar with Kolmogorov complexity? Okay, about 50%. Yeah, the Kolmogorov complexity is the kind of thing which is easy to explain in 1 minute. So I'll just do it. It's like, imagine if I give you some data, or you give me some data, and I'm going to compress it by giving you the shortest program that can possibly exist. The shortest program that exists, which if you run it, outputs your data.
There's a typo.
Oh. Typo.
Okay. Y instead of Y should be X.
Yes, that is correct. You got me. It is the length of the shortest program which outputs X. Yes. Intuitively, you can see that this compressor is quite good because you can prove this theorem, which is also really easy to prove. Or rather, it's easy to feel it. And once you feel it, you could kind of believe me that it's easy to prove. And you can basically say that your Kolmogorov compressor, if you use that to compress your strings, you'll have very low regret about your compression quality. You can prove this result. It says that if you got your string X, your data set, database, whatever, the shortest program which outputs X is shorter than whatever your compressor needed output, and however well your compressor compressed your data, plus a little term which is however many characters of code you need to implement your compressor. Intuitively, you can see how it makes sense. The simulation argument, right? The simulation argument. If you tell me, hey, I've got this really great compressor C, I'm going to say, cool. Does it come with a computer program? Can you give this computer program to K? And K is going to run your compressor because it runs computer programs. You just need to pay for the program length. So without giving you the details, I think I gave you the feel of it. Kolmogorov complexity, the Kolmogorov compressor can simulate other computer programs, simulate other compressors. This is also why it's not computable. It's not computable because it feels very much at liberty to simulate all computer programs. But it is the best compressor that exists. And we were talking about good compression for unsupervised learning. Now let us generalize a Kolmogorov complexity, a Kolmogorov compressor, to be allowed to use side information. Oh, more than detail. So I'll make this detail. I'll reiterate this point several times because this point is important. Obviously, the Kolmogorov compressor is not computable. It's undecidable. But hey, because it's searches over all programs. But hey, did you know that if you run SGD over the parameters of some neural net with 100 layers, it's automatically doing program search over a computer which has a certain amount of memory, a certain number of steps? It's kind of like micro Kolmogorov, fitting a neural net. You kind of see the feel, the similarity. It's kind of magical, right? Neural networks can simulate little programs. They are little computers. They're circuits. Circuits are computers, computing machines. And SGD searches over the program. And all of deep learning hinges on top of the SGD miracle, that we can actually train these computers with SGD. That works. Actually find those circuits from data. And therefore, we can compute our miniature Kolmogorov compressor. And the simulation argument applies here as well, by the way. I just want to mention this one fact. I don't know if you ever tried to design a better neural network architecture, what you'd find is that it's kind of hard to find a better neural network architecture. You say, well, let's add this connection, let's add that connection, and let's like modify this and that. Why is it hard? The simulation argument, because your new architecture can be pretty straightforwardly simulated by your old architecture. Except when it can't, those are rare cases. And in those rare cases, you have a big improvement, such as when you switch from the little RNN to the transformer. The RNN has a bottleneck, the hidden state. So it's a hard time implementing the transformer. However, had we found a way to engineer an RNN with a very, very large hidden state, perhaps it would become as good as a transformer again. So this is the link. You start to see how we switch from the formal land to neural network land, but you see the similarity. So conditional Kolmogorov complexity as the solution to unsupervised learning. You can basically have a similar theorem where I'm not going to define I'm going to define what k of y given x is. It's like the shortest program which outputs y if it's allowed to probe x. That's the length of that shortest program which outputs y if it allows to probe x. And you can prove the same result. And you can see immediately that, yeah, this is definitionally the solution to unsupervised learning. If you use that, you can sleep very, very safely at night, soundly at night, knowing that no one does unsupervised learning better than you, right? It's literally that. So this is the ultimate low-regret solution to unsupervised learning, except that it's not computable. But I do think it's a useful framework. And here we condition on a data set, not an example. And this thing will extract all the value out of x for predicting y. The data set, not the example. So this is the solution to unsupervised learning. Done. Success. And there is one little technicality which I need to spend a little bit of time talking about, which is, we were talking about this conditional Kolmogorov complexity, right? Where you are talking about compressors that get to see, try to compress one thing while having access to another thing. And this is a bit unnatural in a machine learning context when you care about like fitting big data sets. At least as of today, although it's changing fairly rapidly, but I think it's still fair to say that there is no truly good way of conditioning on a big data set. You can fit a big data set, but you can't condition on it, not yet, not truly. So this result says that, hey, if you care about making predictions about your supervised task y, using the good old-fashioned Kolmogorov compressor, which just compresses the concatenation of x and y, is going to be just as good as using your conditional compressor. There are more details and a few subtleties to what I just said, and I'm happy to talk about them offline in the event someone is interested in them. But that basically says that if before you're saying, hey, the previous slide said that you can use this conditional Kolmogorov compressor to solve unsupervised learning, this says that you can also use your regular Kolmogorov compressor. Just throw all your data, take all your files, concatenate them, compress them, and that's going to make some great predictions on your supervised task, the task that you care about. There are some intuitions about why this is true. This result is actually like, proving this is slightly more tricky, so I won't do it.